16 in your survey textbook. Okay, so right now we will continue our lessons on the next chapter. Okay, so let me share the slide first. Okay, the topic will be the electric current and the direct current circuits. Okay, so it will be a electric current and a direct current circuits. Okay, so in this chapter, okay, we will have a few units of chapter. Let's say if you notice here, we have electric current. Okay, we will learn about electric current. Before this, we already learned about electric charge and electric potential. So now we want to complete the Ohm's law. So we already have electric potentials, and right afterwards, in this part we learn about current and also resistance. Okay, so first is electric current, and then we will learn about resistance, and then we will complete the V equals to IR. Okay, V equals to IR, and of course we want to learn what is the Ohm's law. Okay, and then we want to see the energy and the power from the electric circuits. Okay, of course we want to learn about resistors in series and parallel. Okay, resistors in series, so how can we combine the resistors in series and also in a parallel. Okay, and this is quite new to you. Okay, a Kirchhoff rules. Okay, which what is the Kirchhoff rule, what is behind the Kirchhoff rules. Okay, we will learn later. Okay, and of course we will complete the chapter with the capacitors. Okay, the capacitors, which we will combine all the capacitors in series or parallel. Before this, we already learned about capacitors, but in terms of electric potential and electric potential energy, meaning that we learn about V, we learn about electric potential and also charge. The capacitors equals to Q over V. So right now, we want to learn about capacitors, but how can we combine capacitors to the electric circuits? Okay, and of course, we can touch a bit of RC circuits. So what is RC circuits? And of course, the applications of ammeters and voltmeters. So this should be units of chapters for our next lesson. Okay, so the learning outcome will be like this. State and define the terminologies, concepts, laws, and principles in the area of electricity, verbally, visually, and algebraically relate, discuss, explain, okay, and identify the access and apply the concepts of laws and principles in electricity. Okay, now see, we can see a lot of states, and we're verbal. Okay, maybe we have defined, maybe we can identify, we can assess, and we can apply the concepts of what we learned in before we can come to the conclusions, right? So what is electric circuits? All right, so this is story about electric current. So first of all, okay, if you want to know what is electric current, then we should define current in terms of a quantity of charge per unit time. Okay, you can see here the definitions of electric current is the delta Q over delta T. Okay, delta Q over delta T. You know, Q is charge, quantity of charge, and delta T is the time, a total time. So you can say that the flow of electric charge, okay, from one place to another, okay, in the presence of time. Okay, in the presence of time, of course. So you make sure electric charge. We want to make sure in the first chapter, 15, okay, we learn about electric charge. Okay, electric charge meaning the electrostatic charge. That means charge doesn't move. But on the second step, or on the electric potential, or in the second chapter of PHY 098, we learn about how can we move charge in the electric field. Okay, just move the charge and we can see the electric field lines, equipotential, and so on. But in here, we will learn about electric current. Okay, when we want to learn about electric current, that means we want to make sure that the electron, okay, the charge, okay, specifically electron, okay, move as a function of time, okay, as a in the presence of time. So that's why we can say that I equivalent to Q over T, okay, quantity of charge per unit time. And you know the quantity of charge have a unit of coulomb, C, capital C, and of course time is second. So you can say that the coulomb per second is equivalent to ampere, okay, a capital A. Okay, this is ampere, right? Ampere, right? So that will be the unit for current. Current will have ampere. Okay, it means that if you notice A, okay, 10A, that means 10 ampere. So 10 ampere is actually 10 coulomb per seconds. Okay, 10 coulomb per unit second. So that's how they interpret ampere. Okay, and if you want to notice the electric current, okay, first of all, you need to see the circuits with a diagram of the flashlight here. Okay, you can see here, if there is no current, then we cannot see a bulb will flash, okay, or a bulb will switch on. Okay, we are saying that the current is the flows of electron per unit time. But what is the properties of the electron? What is the properties of the current? First of all, it must have a closed path. Okay, what is the closed path? Okay, we can see that which the charge can flow returning to its starting point is called electric circuit. So electric circuit is a closed path. So this should be the electric circuit. This is a very simple electric circuit that we can have. Okay, from here we can see, you see, this is the batteries, which have a positive plate and also negative plate. Okay, or in your terms, you will call as positive terminal and to negative terminals. Okay, this is the switch. Okay, and of course, this is the bulb. Okay, bulb is like a certain wires that we have that have a resistance, and it glows. Okay, it glows when it reach a certain resistance, okay, due to the presence of the current. Okay, so bulb is actually a wire, okay, a wire, okay, that have been had that have glow during the excessive electron that move throughout the electric circuit, the closed path of electric circuit. So we are saying that the current will move in a manner of from the positive terminal to the negative terminal. Okay, current will move from positive terminal and goes out from the positive terminal and it comes back from to the negative terminal. Okay, so in this chapter we only consider a direct current circuit. So what does it mean by direct current circuits? Okay, which means, okay, we will direct current circuit is also called as DC. Okay, DC. What is direct current circuits? The flows of current only come from positive terminal into negative terminals. Okay, and it cannot do irreversible current flows. Okay, the issue comes from the positive terminal into the negative terminals. That's all. Okay, so that's what I mean by a direct current. Okay, so the directions of current comes from positive terminals. As I'm saying just now, comes from the positive terminal. Look at that, the presence of batteries, and we are saying that. So the batteries come with this kind of figure. Okay, you can see here we have a longer plate. Okay, longer plate when we used to sketch a symbol of the batteries. Okay, make sure you have um, one one terminal should be longer compared to the other terminals. So the longer one should be positive, and the other one will be negative. Okay, right. Make sure the positive and also negative. And the current will goes from positive terminals and comes back into negative terminals. And that should be the flows of current that we are talking in the direct current circuits. Okay, the directions of current flows in the direction in which the positive charge, the positive test charge will move. Okay, so we are saying that the positive test charge, okay, currently will be a lot at the positive terminal, will goes, okay, will goes up in terms of the electric current. Okay, so we are saying don't fall into the trap of positive charge. Okay, because the one that should flows in the electric current circuit should be the electron. Okay, and we know the electron a lot will be at the negative terminal. So we can have here negative a lot of electron. So the electron of the flows of electron should be from the negative terminal, and it will goes to the positive terminal because the electron should meet the positive charge. Okay, so in this case we are saying that the directions of current, okay, is actually against the directions of flows of electron. That, yeah, you should know about the theoretical part of in the electric circuit. Okay, the flow of electrons and the current arrow point will be opposite to each other, right? So the directions of current comes from the positive terminal and goes to negative terminals. But when they ask you about the flows of electron, okay, look here, this is electron, this is current. They're two different things. Although if you want to make if you want to make a current, you must have a flows of electron. Remember, okay, that we must have a flows of electron in order to have a directions of current. In order to get the current, you must have electron. Okay, but the beautiful case of the current and also electron, they both are against each other. Okay, the electron will move from the negative terminal to positive terminal. Otherwise, the current will move from positive terminal to negative terminal. Okay, so that is will be the in terms of macroscopic. Macroscopic means on the big, okay, big coverage of the electric circuits. Okay, but right now we want to know what's happened inside the beautiful wires. Okay, what happened inside if you do have wires, if you do have a electric circuit, let's say this one is a wire that we magnify it. Okay, when magnify, we can see a electron move inside here. Okay, we can see with another colors here. You can see the electron that happens to be in the wires. What happened to this part? Okay, so this is called a microscopic view. Okay, a microscopic. Okay, micro means smaller. Okay, in a smaller scale, what happened inside the wire itself, right? So we want to know what happened in this. So on the macroscopic, current can be related to the motion of microscopic charge carriers making up the current. It turns out that current depends on the average speed of charge carrier in the directions of current. Okay, okay, average speed of the charge carrier in the directions of current, the number of charge carrier per unit volume, and the size of the charge carrier by each. Okay, now you can have three things inside the current. Okay, when we talk about current, first you must have an average speed. Okay, average speed of the charge carriers. And number two is we must have a number of charge carriers per unit volume. Okay, number of charge carrier per unit volume, and in the end we'll have the size of the charge carrier by each. Okay, so right now, okay, now please focus on this part. Okay, you will know that I is equivalent to a delta Q over delta T. What is delta Q? So in our terms, at the macroscopic view, macroscopic view, bigger view. So we are saying that delta Q is just a magnitude of charge. Okay, magnitude of charge, a number of charge. But in terms of microscopic view, so we should remember things. Okay, delta Q is based on the number of carriers and times with the charge per carrier. Okay, so it will give you a certain number. So what is the number here? So we will have n, okay, and we'll have e, and we will have delta x, okay, and times with q, right? So and q is what is the charge per charge of the each carrier, okay. And if the carrier move with a constant average speed called drift speed, see, we can have a drift speed. So what is the drift speed? The distance they move in is the time interval delta t. So we will have, okay, let's say Vd is the drift speed comes from delta x over t, okay, delta x over t. So again, here delta x over t, so we can say that delta x itself is vd times t. So that's why vd times t we can put inside here. Let's look, if I write down differently, we can have a and we can have delta x, okay, with the bracket and then times q. Okay, can have delta x and times q. But delta x itself is stands for Vd times t here. And you can bring to this part. Okay, so that's why we can replace the delta x with the Vd times delta t or Vd times t. And Vd stands for drift speed. Okay, drift speed. Why we call that as drift speed is because of we are in the microscopic view that we can say that the speed of the charge is very discrete. Okay, very small value, but very fast. That's why we are saying, yeah, we can have a drift speed. If if the question asks you what is the speed of the charge, then you can find using this equation. The drift speeds, the distance they move in, the time interval delta t, okay, is called, then we can write down as delta q. It is equivalent to, all right, and a is the area, all right, and it's the number of moles, okay, times with delta x, right, and times with q or delta x, okay, we can define it as using drift speed times t. Divide with, now remember, okay, we can put inside here, okay, I try to write it back, okay, we write it down, I equivalent to delta q over delta t, and we can write down as n a vd delta x delta t, sorry, vd delta t times q over t. So we can cancel out delta t and t. So in the end, we will have n a vd q over the equivalent to I. So we can define current in terms of, maybe this one is the macroscopic, this one is for macroscopic, and this one I equals to NAVDQ is equivalent to microscopic. Okay, micro and macro. So you can have two things or two equations for current itself. I can be represented by macroscopic, which is delta Q over T, and okay, we can have a microscopy. We can see, you can look afterwards what kind of problems that we are facing if they want you to know about microscopy. Okay, let's go to the parts where we want to find what is the microscopy. Okay, right, the amount, let's say example 17.1 from your survey textbook. Okay, the amount of charge that passes through the filament. Okay, the filament, meaning that this one have bulk of a certain bulk. Okay, in 2 seconds is 1.67 coulomb. Okay, this is what? This is Q. Okay, this one is time. Okay, try to do it like what I'm doing just now, because if you want to get to know these things, make sure you know everything. Okay, so first is find the average current in the light bulb. Okay, the average current, find the average current. So the meaning that we have Q, we have T, so we can define I equals to Q over T. Okay, 1.67 divided by 2 seconds. Okay, remember times in seconds. Then we can have 0.35 835 ampere. Okay, so that is number one. All right, so look at this question B. Okay, find the number of electron that pass through the filament, the number of electron that pass through the filaments. Okay, so right, so if you want to know about the number of electron, we cannot easily get with Q, because Q is the magnitude of charge. When it comes to the number of electron, remember this one will focus on the microscopic view. Okay, this one will focus on microscopic view. So first of all, start with the R equals to Q over T, and remember Q is at the microscopic it will becomes, okay, N times Q. Okay, N times Q. So N is called a number of electrons. So in our presence, this one, okay, this part, okay, if you look at this part, okay, I will circle this one, okay, with green color. This one is the number of electron. The number of electron times with the charge of the electron. Number of electron times with the quantity of charge. The number of electron times with the charge. So that's why we are saying that NQ over, NQ over T. Okay, so we want to know about N. So N is what? N is equivalent to, okay, I times T divided with Q. Okay, I times T divided with Q. And remember, this is the number of electron. Okay, how can we get this one? From the from the microscopic view. Remember, microscopic view. Why? Because we want to know the number of electrons. Okay, number of electrons. IT, so meaning that we can have current. Okay, from the first from part A, we can have current, we can have time, and Q is the charge of the electron, not charge from the question. Okay, it's not 1.67 coulomb. Okay, but instead we should put a Q as value of 1. Okay, remember Q is 1.6 10 power of negative 19 coulomb per electron. Okay, but remember, don't mind about electron, but it's just a coulomb, so we can replace this one at Q. Okay, so in the end, we can have 2 times 2.61 times 10 power of 19 coulomb. Okay, 19. Sorry, electron. So that will give you the number of electron. Okay, right. So let's look at the next part. Okay. If the current is supplied by a 12-volt batteries, okay, 12-volt batteries, what total energy, okay, look at the question, what total energy is delivered to the light bulb filament? Remember from our previous lessons, U will be the total energy is equivalent to QB, okay, U equals to QB. So for the filament have 1.67 charge. So you can replace this one with 1.67 coulomb, because it doesn't involve any electron here. Okay, it doesn't involve. It now turns back to the real question, which is the filament. Filament contain 1.67 coulomb of charge. So V, how about V? So V is 12-volt batteries times with 12. So you can have 20 joule. Look at the unit use, joule. for energy, right? And and the last part will be what is the average power? Okay, what is the average power? So again, okay, we can use energy over time. So because power is basically okay, energy over time. So energy is what? Is we can use a potential energy. So we can get 20 divided by 2 is equivalent to 10 watt. Okay, 10 watt. Right? So that's how they get the answers for all questions. Okay, so this is a very good examples. Okay, you should highlight it. Please redo. Please redo. Please get your focus on the questions where they have a lot of things to cover inside the question itself. Okay, a lot of things that you can understand from this part. You can understand first the electric current equivalent to Q over T. And you can also know electric current is also equivalent to NQ. Okay, electric current I equals to times NQ over T. NQ over T. Remember, I equals to NQ over T. It's not a capital Q, it's a Q. Q of the charge of the electron. Because this is specifically for electrons. So that's why the question asks you about the number of electron. This is the number of electron. Okay, right. So look at the second examples, right? The disk drive in a portable CD player is connected to a battery that supplies with a current of 0.22 amperes. So this should be current. How many electrons? Look at the questions. How many electrons pass through the drive in 4.5 seconds? This should be time. Okay, how many electrons? They want to know about n number of electrons. How many electrons? Okay, so remember I equals to okay NQ over T. So you have I, you have T, and you also have Q. So remember you can find n. So in the end, they will use n. In this question, okay, they replace Q with E. Okay, doesn't matter as long as you understand that Q or E is just the magnitude of electron, okay, which is 1.6 10 power of negative 19 coulomb. Okay, right. So let's look another examples. Okay. The examples are about drift speeds of electron. So when we talk about drift speed, definitely, yeah, we will calculate that involve a microscopic view. Okay, let's look at the each examples thoroughly. Right. So a copper wire of cross-sectional area. Okay, have a cross-sectional area. So this should be your A. Okay, carries a current of 10 amperes. So this should be I. Assuming each copper atom contributes one free electron to the metal, find the drift speed of the electron in the wire. Find the drift speed of the electrons in this wire. Okay, each copper atom it contributes one free electron. Okay, one free electron. So meaning that from each copper atom it can contribute one electron. Okay, we have a lot of copper in the presence of cross-sectional area, but we want to know okay what is the drift speed. Okay, remember, so it starts with the I equals to Q over T, but at Q we can replace it with NQ over T, and of course at N we can replace it with the N A VD. What is VD? The drift speed times with T, okay, times with Q over T. And we can cancel out T and T. So in the end, we will have NAVD times Q for I. Okay, but then again, we should remember that we don't have N. We don't have here, we have A, we have Q, we doesn't have N. So how can we get N? Okay, N is what? N is considered as a number of mole. Okay, a number of mole. So how can we define N? Right. So as stated in the examples here, that n will come at the very best of here in the box. That n is the number of Avogadro over number of mole. So how can we get on this side? Okay, so from this side, it comes from the densities. Okay, the formulas of density, which we have done rho over m over v. Okay, rho is equivalent to mass per unit volume, but we want to know what is the volume. So volume equivalent to mass over rho. Okay, mass over rho. And if you notice in the question, the density of copper is 8.92. Okay, density of copper 8.92 gram per centimeter cube, and its atomic mass is 63.5 U. 63.5 U. All right, so we can convert it to gram. Okay, in which we can have a mass of 63.5 gram over 8.92 gram per centimeter cube. Okay, because it should be here centimeter cube, then we bring up to here, and then gram and gram, and then we can have a total number of 7.12 centimeter cube as the volume. Okay, at that volume, okay, we can use that inside the number of Avogadro in order to get the number of mole. Okay, the number of Avogadro per mole times with 7.12 10 power of negative 6 meter cube per mole. So we can cancel out the electron, the mole, and we left with the electrons per m cube. And in the end here, we get 8.46 10 power of 28 electrons per meter cube. And okay, we can put it inside the equations. Our equations want us to find I equals to N A VD times Q. So we want to use VD. So VD is what? Okay, VD is I over N A Q. Okay, N A Q. So this is N. Okay, this is N. This one is Q. And this one is what? A. And then we can have a grid speed like this. 2.46 10 power of negative 4 meter per seconds. Okay, very good. Just do your part on part A, because on the part B, they will use a ideal gas model to compare the grid speed with the random RMS speed. Okay, you know. Okay, you will learn this later when you learn about alternate current. Okay, the RMS stands for root mean square. Okay, root mean square. Right? So although electrons move freely in metal wires, they do not flow unless the wires are connected to the source of electrical energy. Okay, a close analogy is provided by water in a garden. So if you do have, right, if you look at the figure on the left, you can see that the equal potential energy, but it cannot flow because there are some the potential energy is equal from point to point. Okay, but when we have one high potential and another one is low potential, then we can have a flow of water on the figure B. So that's how they do some analogy in terms of how can electron move in the metal wires. Okay, it's due to the electric potential. That's why we are saying potential difference. You must have a potential difference in order to make the electron flow. Okay, the electron cannot flow if the potential are the same from one point to one point. Okay, 10 ke 10. Okay, you cannot do like that. Okay, we are saying if the potential are the same, there is no electric flow. But the electron will flow if the electric circuit have a high potential energy to low potential energy. So that is very good analogy in terms of how can electron flows. Okay, A battery uses chemical reaction to produce a potential difference between its terminal. Okay, between its terminal. So from the perspective of the battery itself, okay, we will have a positive and negative terminal. If you look carefully, these are the positive terminal of the batteries on top of the battery. Because normally we used to see a lot of batteries like the one that we have in here. Okay, on the right figures, you can see this is the usual or the common batteries that we always see. Okay, okay, we will see the positive terminal on top of the batteries, and of course, the negative terminal is on the bottom part of the batteries. Inside the batteries, then we have an electrode and also electrolyte. So this is the electrode, and this one is the electrolyte. And they will use a lot of oxidation and reduction process in order to produce a certain movement of the electron. Okay, the terminal correspond to a high electric potential is denoted by positive, where the terminal correspond to the low electric potential is denoted by negative. When the battery is connected to a circuit, electron move in a closed path from the negative terminal of the batteries through the circuit and back to the positive terminal. So remember, okay, electron move in a closed path from the negative terminal to positive terminal. That is electron. Okay, but the current comes from positive to negative. Okay, remember one thing. A battery that is disconnected from any circuit has an electric potential difference between its terminal that is called electromotive force or EMF. Okay, when any circuit disconnected from any circuit, a battery that is disconnected from any circuit has an electric potential difference. Right, so that is something you want to know. This is how they connect the batteries. Okay, and of course, look at the simple usage of electric circuits. Okay, maybe this one later on when you come to our lab, then you will get to know how to connect between a bulb, an ammeter, or voltmeter. Okay, if you can look here, ammeter is the one that you should put inside the electric circuits in order to measure the current. Measure the current. Okay, this one is for measuring the current, measuring I, and voltmeter is for measuring V. Okay, measuring the electric potential or voltage. Okay, a lot of names for voltage. Sometimes we call it as a voltmeter. Okay, also we call it as volts, voltage, and maybe potential different, electric potential, all are the same. Okay, so the one that we can measure the electric potential is voltmeter. Okay, and how to connect a ammeter and voltmeter. So the one that we have now, okay, we cannot put ammeter at voltmeter at ammeter from the single circuit. Why? Because a voltmeter will measure the voltage or electric potential, but ammeter will measure the current. Okay, we'll measure the current. So how can we get the current using here? All right, so let's say you have batteries up there with the positive and negative terminal. So you can see here, these are the flows of current, and not flows of electron. We are not talking about electron anymore. Okay, when we talk about current, so the flows will comes from the positive terminal into the negative terminal. Let's say it goes here and it comes to this part. Let's say point A. Okay, in my figures is point A. When it comes to the point A, okay, it will split up. The current will split up because it made A. A is what? It is called as junction. Why we call that as junction? Because it have two or more than one root. Okay, so in order to pass through to get to the negative terminal, so it will meet the junction. At this junction, the current will split up. It will split up, okay, to the bulb and also to the voltmeters. And if the current move from this point A to point B, and afterwards, okay, the current will meet up again at point B, and together they will move across the emitter and goes back to the negative terminals. So that's how current move. Okay, when they meet the junction, it will split up. Okay, we don't know whether 50-50, maybe a 70-30, 80-20. That is depending on the current and on the voltage, right? So that's how you know. And of course, if you look carefully, the emitter will be connected to the electric circuits in parallel and sorry, in series to the bulb. But the voltmeter, okay, will comes straight to the bulb. So if you want to measure the voltage of the bulb, then the voltmeter will goes here and then put the value here. It's like a hand, and we touch the bulb from one point A to point B, then we can measure the voltage or electric potential. Okay, so as conclusion, emitter, okay, will measure the current, and voltmeter will measure the electric potential or voltage. Okay, all right. So I think we will break. We'll take a break for a few minutes, then we will continue later. Do you have a question?
So the voltmeter measure the volt and potential energy, right?
Okay, not electric potential energy, just electric potential. Okay, yes, correct. Okay, so let's continue our lessons. Let me share the screen first. Okay, so right now we want to learn about resistance and Ohm's law. Okay, resistance and Ohm's law, right? So normally we will talk about resistance. Okay, this is the resistance. All right, we already talk about current. We already talk about electric potential. Now we will complete the Ohm's law with the presence of the resistance. And under normal circumstances, wires represent some resistance. Okay, and of course what it will resist the motions of electron. In order to get the electricity, or we want to make the if you want to make the current flows, okay, we must have a resistance. Why? It's quite quite complicated in terms of defining resistance, because when we talk about current, okay, normally, if there is no resistance, then the current couldn't move. Okay, the current cannot move inside the electric circuits. As simple as that. Okay, in order for the current to move, it must have the flows of electron. Okay, if the electron doesn't move, then the current can not also move. So that's why we need to have a resistance, because without resistance, there is no possibility of current to flow. Okay, so that's how it relates to the current and resistance. And of course, the complicated part will be we cannot say that if you have a flows of waters using a tube or what, so the flows of water will flow will flows better if there is no resistance. That is in terms of water, but this one is not water. In fact, this one is current. If current must have a resistance, okay, current must have a resistance, right? It must have a resistance to flow. Okay, share slide again. Okay, right. So the Ohm's law stated that V equals to IR, but actually the Ohm's law stands for R, that equivalent to ratios of V over I, the ratios of voltage over current, or electric potential over current. So that is how we can interpret Ohm's law. Okay, the Ohm's law is the where we want to see the ratios of voltage over current, right? And if you happens to memorize this one, because the easier part will when we talk just V equals to IR. So that is how V equals to IR stands for Ohm's law. But it's basically comes from the resistance equivalent to voltage over current. Okay, voltage over current, and the unit for resistance is ohms. Okay, the unit for resistance is ohms. While here voltage, okay, or electric potential is volts, and the current will be, so this one is volt, and current will be ampere. So volt per ampere, you will get ohms, OHM, ohms. Okay, so that's how they get the Ohm's law, right? So solving for the resistance, we find that R equals to V over I, as I mentioned earlier. So what is 1 ohm? So 1 ohm is considered as 1 volts per ampere. 1 volt per ampere. Okay. And if two wires have the same length and diameter, will have a different resistance. Okay. So resistance will depends on a lot of factors. Okay, resistance of course will depends on a lot of factors. The first of all is the length. And you can see the diameters, and maybe because of the materials itself. Okay, so in that part we can say that the properties of the resistance is called resistivity. Okay, the properties of the resistance. So in the end, okay, we can also define the resistivity role is equivalent to here. Okay, the resistance is equivalent to rho L over A, where L is the length of the length of the wires, or length of the diameters, length of the wires, and ampere is a surface area of a wire. And of course, here it's like rho is not a density. In fact, rho is a resistivity. Okay, resistivity, meaning that that is the properties of the resistance. Resistivity is the properties of the resistance. Okay, we can see here, these are the difference between insulators, semiconductors, and conductors in terms of resistivity. You can find here, so this part is where we have this part is a okay, more to metals. Okay, this part is the semiconductors, and last part will be the insulators, or the one that on the right tables you can see a difference between insulators, semiconductors, and conductors. Okay, there will be a lot of, and mostly, okay, insulators will have a greater resistance, okay, a greater resistance compared to uh, conductors and semiconductors. Okay, you can look at the value. Resistance will have a greater value compared to insulators will have a greater value compared to conductors in terms of resistivity. Okay, so you will have to remember, memorize this. Yeah, it will be put inside your questions. Don't worry. Okay, let's look at the examples. A current of 1.82 amperes flows through a copper wire 1.75 meters long. So this one is I current, and the copper wire is what? This one is L, and 1.1 meter in diameter. Okay, this one is D. Okay, D is the diameter. So meaning that from D diameter we can have R. And remember, normally a wire will be in the form of like this one, a circle. Okay, a circle. So the cross sectional area is pi r squared. Okay, or maybe you can define this one as pi d over pi d square over 4. Okay, because d, how can we get pi d square over 4 like the one on here is based on r is equivalent to d over 2. Okay, so if r squared, then this one d square over 2 also square. Then of course you can have d square over 4. So that's how they get d square over 4. Okay, so find the potential difference between the in the end of the wire. Find the potential, uh, find the potential difference. Okay, between the end of the wires, right? And the value of the value of resistivity for copper may be found in the table. So we need to get the value from the table in your books or in the given appendix. Okay, so you first using the resistivity, R equals to resistance, resistivity L over A, right? We have length, but we never have A, so A is considered as pi d square over 4. Okay, like I did just now. Okay, you can use this one times with pi. Okay, in order to get the resistance. And after that, if you manage to get the resistance, then you times with the current. Current is 1.82, and in the end, we will get 0.0577 volts. Okay, so that's how they get access. Okay, in general, the resistance of material goes up as the temperature goes up due to the thermal effects. Okay, this property can be used in the thermometers. Okay, the resistivity decrease as the temperature decrease. Okay, so the resistivity due to the presence, the resistivity will depends on the material. Okay, every material have different resistivity. So that's why we can have a bigger insulators. As insulators have a bigger or a greater value of resistivity compared to conductors. Why? Because the presence, the arrangements of atom, the temperature, everything will be considered. Okay, so that's why we are saying that the resistance of material goes up as the temperature goes up. This happens to be for all materials. Okay, temperature will goes up as the resistance will goes up as the temperature goes up, and of course the resistivity decrease as the temperature decreases. Okay, all right. So this is where we get the energy and power in electric circuits. Okay. As usual, U equals to QV. Remember, U equals to QV from our previous chapter. QV, Q is the magnitude of charge. Sometimes don't get confused between a capital Q or small letter q. Okay, don't get confused between that because it's just a Q. It's just a magnitude of charge. But sometimes we have to differentiate between a capital Q and small letter q, especially when you try to dealing with something that regarding microscopic or macroscopic. So that part, okay, please make sure you use it correctly. Right? So V is always a capital letter V. Okay, so Q is the magnitude of charge times with the electric potential. And if we try to bring out in the power, power is E over T, remember, and E is the also U over T. So what is U? QV over T. Okay, QV over T. And remember, QV is what? Q over T is considered as current. Okay, remember, magnitude of charge per current. So that's why we can get P equals to IV, where I is the current and V is the voltage. I will use here voltage. Remember, sometimes they didn't call you voltage, but they call it as potential difference or maybe electric potential. But that is all the same thing. Voltage, electric potential, and potential difference. That. Don't get confused between the terms. Okay, so that will be the electric power. Electric power based on the current and voltage. P equals to IV. The unit will be watt. Okay, from the Ohm's law, if we manage, remember Ohm's law is R equals to V over I, and of course V equals to IR. Then we can replace this one. We can replace V equals to R inside here in order to get P equals to I square R. Okay, I times I with R, so I square R. And also you can replace, okay, I, let's say here, from here, you can replace I equivalent to V over R. Yeah, you can replace I, okay, using V over R. So you become V square over R. That will depend. So right now we have P equals to IV, P equals to I square R, and P also equals to V square over R. So you have three different approach to get the to calculate the value of power. There is either P equals to IV, I square R. So that will depend on the situation of the questions. Okay, maybe at one point you will not be given a current. So how can you calculate power? Yes, you can calculate power using voltage and resistance. So using this equation. So that will depend on the situation. Okay, because that will in the first example doesn't have R, and the second example doesn't have V. On the third equation doesn't have I. So that will give you three different approach in order to get the power. All right, so let's look at this example. The circuit consisting of a battery and a resistors. Okay, so this is a battery and this is a resistor. Okay, this is a one simple electric circuits that can we have, because it contains in the V, it contains electric potential, and it contains R. So V equals to R, then we can see this circuit will follows the Ohm's law. Okay, the circuit consisting of a battery and a resistors is shown in our sketch. Okay, 12 volt and also 545 ohms. We show the current flowing from the positive terminal of the 12 volt battery through the 545 ohm resistor into the negative terminal of the batteries. Okay, the example is the question is how much energy is dissipated in the resistors in 65 seconds. So you have volt, you have V, you have what? This one is R, and this one is E. Okay, and of course, how much energy? How much energy is they want to find U? What is U? Or maybe what is uh, E? Okay, potential energy U or E doesn't matter. So how to get that part? Okay, remember E is equivalent to P times T. So we need to find what is power. But if you're not to do that, we need to find power using V and R. So P what? P equals to V square over R. Because we doesn't have I, we doesn't so we need to get the informations from the questions only, okay, without using any because we want to reduce the mistake. If you are managed, let's see, first of all, you find, you try to do this way, V equals to IR, maybe you want to find I, what is V over R, okay, get the I first, and then you get P equals to IV. That is okay. It's still you can get the right answers, okay. Here, let's see if you have I equals to V over R, and then you occasionally try to find P. Okay, that is also true, but that requires you to get I. And I cannot guarantee that you will have all you will always be right in terms of calculating I, because sometimes, okay, there will be time, okay, uh, nauzubillah, okay, there will be time that you can make mistake. You can make mistake, okay, you can make mistake, and if the I is wrong, and if your answer is I is wrong, then you cannot have the correct value for power. So that will be shame. And of course, because we can easily get power from the questions, the information inside the question. You have V, you have R. Use that value. Okay, don't try to find I, because I is not I is not considered as correct yet. Okay, and when we get I, we times with V is of course. Okay, but right now use the one that they give you inside the questions. Okay, that is maybe more possible things to do when you're being given the information. So V square over R, get the P, and of course times with T, 65 seconds. So the answer should be 17 joules. Okay, this is very good examples on how you can determine and how you can get the value. Okay, all right. So when the electric current send you a bill, your usage is quoted in kilowatt hours. Okay, so this should be how can you calculate your usage of electricity. Okay, they are charging you for energy use, and the kilowatt hour are measures of energy. Kilowatt hour. So kilowatt hour. So kilowatt is stands for power, and hour is stands for time. So PT is actually E, energy. So we are currently measuring energy, because we are not calculating power, because power is E per T. So E is equivalent to PT. Okay, so what is stands for power, and hour is stands for time, So what? This is 3600 second. That will give you 1 kilowatt hour. Okay, is equivalent to 3.610 power of 6 joule. Okay, these are the SI unit for energy, joule. Okay, 3.610 power of 6 joule. Okay, let's look at this example. A holiday goose is cooked in the kitchen over 4 hours. Okay, 4 hours. So that will give you time. Assume that the stove draws a current of 20 amperes. So this should be I. Operates at a voltage of 220 volts. So this should be electric potential. Use electrical energy that costs 0.068 per kilowatt hour. How much does it cost to cook your goose? Right. So it's given to us V, I, and T. So normally when we have P, V, and I, and we want to know about how much does it cost. So remember, the costing should be energy. Energy is due to PT. So in order to do that, T is already there, but you need to convert it to seconds. Okay, so it's quite simple. That's just find what is P. So P is a power equivalent to IV. So first of all, you have I 20 times with the 224 volt. You can have 4.4 kilowatt, and then okay, use the energy equals to PT. 4.4 times 4 is 17.6 kilowatt hour. So normally, okay, if you don't have any ideas what is kilowatt hour, then you don't have to. You can change it to second. Okay, maybe you can put it in you using joule. But of course, okay, we need to see the questions. The question is asking, or the question is given 68 seconds, 68 seconds per kilowatt hour. Okay, is 0.068 per thousands per kilowatt hour. So we can leave the 4 hours there so that when we calculate 4.4 kilowatt, you look at the value. Okay, the value should be 4,400 watt. But because of we want to tally it with the kilowatt hour, so we change this one to 4.4 kilowatt. And then you times with the 4 hours to get 17.6 kilowatt hour. And of course, the 1 kilowatt hour is equivalent to 0.068 dollar. So in this case, we need to pay $1.2, okay, in order to cook the goose, right? So it's very good examples on determining the usage of the electricity. Okay, the usage of electricity. Okay, now we move to the other part. Okay, so this is about resistors in series and parallel. Okay, before this we learned about resistance, which equivalent to V over I, and here we also learn about resistivity that involve resistivity L rho L over A. A lot of resistors. So that right now we want to learn about the combinations, okay, the arrangements of the resistors in series and parallel. How can you connect the resistors to series and parallel? Okay, so look at the simple connections in here. Okay, a simple connections. We are saying that resistors connected end to end are said to be series. End to end. So what is end to end? Okay, end to end meaning that you have a let's say one resistors. Okay, let's say at point A. Okay, and then from that resistor A, let's say don't use point A. This is resistor A. Okay, resistor A, okay, connect with the resistor B and connect with the resistor C. Okay, how can we combine that? in one particular electric circuit. So normally we'll put that the resistors are said to be in series when it combined end to end, hujung ke hujung. Okay, end to end meaning that from A, after we finish A, then we continue with B. After continue B, then we continue with C. So this is A, this is B, and this is C. So this is the one that we can, okay. So we can represent A, B, C. So the resistors of A, B, C, or maybe R1, R2, or R3 will depends on how you connect it. Okay, because we can have resistors in series and parallel. Okay, resistors in series and parallel. Okay, since the current through the series resistors must be the same each. Okay, and the total potential difference is the sum of the potential difference across each resistors. We find that the equivalent resistance is like this. Okay, so in series, okay, let me replace one. Okay, in series, I same I is the same throughout the electric circuit, throughout the circuits. So meaning that I that comes from the positive terminal, let's say it comes with the 8 ampere and it will come back with the 8 ampere. So this is I. I is the same. So meaning that I will flow through R1 as 8 amperes and will flows at R2 with 8 amperes and also will flow as R3 with 8 amperes also, because I will be the same under the same road. Let's look at the road. The roads comes from the battery itself, so it just have one road, doesn't have any junction. Okay, meaning that you should know when I note on the previous slide about junction. So what is junction? So let's do some recap. So here is when you connect the bulb. Say this is bulb. Okay, this is voltmeters and connected to uh, ampere ammeter. Okay, remember on the previous slide. So I'm saying that this part, okay, this part is what we call as junction, simpang, a junction. At that junction, so when the current can meet the junction, then it will split up. Okay, it will split up and it will goes back to the normal when it reach another junction and everything will go smoothly. Okay, when the current, as long as it stays only on one road, okay, like the one on these figures, okay, we will only have one current. But when the current reach or meet the junction, then it will split up. Okay, so current will depends on the route, jalan. Okay, like the one here, then we have junction, you'll have two routes. Okay, one is here, let me use this one. Here comes to this point, then you will split up here, here on this part, and it will meet again and it will goes back to the normal one. Okay, at, at point A and point A and point B will have the same current. At point C, yes, the same current. But point D and point E doesn't have the current will not be the same as A, B, and C. Okay, A will be the same value as B, and the current at C is also the same as A, B, and C. Current, okay. Current at A, B, and C will be will be equivalent to each other, while for D and E, okay, D and E, okay, because we need to calculate at different part of the end. Okay, all right. So look at the figures. So the one that we should have the different terms. So the current is the same throughout the road, meaning that current will flows on R1 as 8 ampere. Current will also flows as at 8 ampere at on R2, and current will also flows on R3 as 8 ampere. Okay, but that is all current. So the one that you should change, or the one that have a different value, is what we call as voltage. Okay, because I should another. So I will draw a box like this. So one box is called V1. Okay, another box is called V2, and another box is called V3. The total V will be based on V1 plus V2 plus V3. Okay, so that's why we are saying that I is equivalent to R1 plus R2 plus R3. Why? Because we do have know that V1 is what? V1 is I1 R1. Okay, so V2 is also I, because I1 and I2 is also the same, so I'll just use I1. This one doesn't have to put 1. So I R2 plus with I R3. So we factor the I, and we get R1, R2, and R3. So this should be the R equivalent for the series circuit. R equivalent. Okay, that this is the how can we know that in series. Okay, I is the same, and V total is equivalent to V1 plus V2 plus V3, and so on. Okay, I is the same if always in the root, and R equivalent is equivalent to R1 plus R2 plus R3. So that will be the purpose of resistors in series and parallel. Okay, so this is how they get the equivalent resistance for resistors in series. So our job is we need to really know, to really understand the concepts of current and voltage, because the current will flows from the positive terminal to negative terminal. And if you notice, okay, after we manage to make sure that, okay, uh, we will have the one thing that when we considering solving the problems of the resistors in series. Okay, resistors in series, let's say if you have R1, R2, and R3. Okay, and we managed to get the R equivalent. Okay, so we add everything. Let's say R1 10, R2 also 10, and R3 also 10. So you will have a 30 ohms of resistance. So this should be the combinations. Okay, combinations of R. Okay, and we'll have a I. So I times the R equivalent. So you will get the VT. Okay, you will get the voltage total when I total times R equivalent. Okay, right? So this is one example. Okay, one example. Okay, before we proceed to the examples, let me do one step. Okay, let me show you the tips to answering the resistance in series and parallel. Okay, first of all, you need to understand that there will be a lot of electric circuits. Okay, a lot of electric circuits, maybe they will combine between series and parallel. Okay, it's not just about series alone and parallel alone. No, they will combine. Definitely, they will combine to make your life suffer. So they will combine the series and also parallel circuit together inside one question, and they will ask you to do this part, and this part. So in order to do that, first of all, you need to calculate the R equivalent. This is the first step. Calculate the R equivalent first. So how to calculate the R equivalent? So that will depends on either your electric circuits in series or parallel. Okay, so that is R equivalent. First is R equivalent, then you need to calculate the I total. So what is I total? I total is I that comes from positive terminal. So this should be I total. And it comes back to the negative terminal. So this is negative terminal. So this is also I total. I that goes out from the positive terminal into the from positive terminal to into the negative terminal. So that is considered as I total, because I total will be the I that can be used to calculate everything. That's why current is very important when you try to deal with resistance in series and parallel. Of course, okay, this happened that you already learned this part in your secondary school. Doesn't matter. Okay, use a lot of theoretical, or use a lot of how to solve the problems of resistance in series and parallel. But in the end, we must know how can we solve the problems of series and parallel using these two tips, which is you need to find what is the R equivalent and also I total. In order to calculate the R equivalent, remember, make sure, okay, last one of R must, okay, series to the battery. This is the one most important tips when you deal with electric circuits. So last one of R, okay, last examples, or last R must be series to the battery. Let's look at the examples here. So we have three resistors in series, okay, three resistors in series, and the last part will be here, R equivalent, also in series. Okay, when we combine R1, R2, and R3, then we can have R equivalent. EQ means equivalent. Okay, R equivalent means kita gantikan ke semua R1, R2, and R3 into only just one single R equivalent. So that's how it means by R equivalent. So R equivalent times I total. So this is I total. I total times with R equivalent to get V total. Okay, remember these things, right? So it's very good for you to understand this both R equivalent and I total. Okay, let's look at the examples. A circuit consists of three resistors R1, R2, and R3 connected to in series to 24 volt batteries. Okay, you have 24. This one is called VT. Okay, the current in the circuit is 0.032. So this one is saying that the current in the circuit, look at the current circuit, okay, does it have any junction? Definitely no. Okay, because this one is not considered as junction. This one is a corner, just a corner of the circuit. It's not a junction. Okay, so you will see that only one single current inside the electric circuit. So that the value will be, this one is I total, 0.032 ampere. Given that R is 250 ohms and R2 is 150 ohms, and R3, okay, find the value of R3. Find the value of R3. Remember, okay, when R3 is not complete, is not given, so they want you to calculate the value of R3 using what? Using R equivalent, because R equivalent is equivalent to Okay, 250 plus 150 plus with R3. And remember, we don't have that value, R equivalent, but we can calculate R equivalent using V total. So V total equivalent to I total times R equivalent. So R equivalent is V total over I total. So what is V total? 24, and I total is 0.032, and in the end we'll get 750 ohms for R equivalent. So 750 volts. So in order to get R3, R equivalent tolak 250 tolak 150, so you will get 350 ohms. Simple. Okay, and the value will be the find the potential difference across each resistor. Okay, find the potential difference across each resistor. So you already know that I will flow from R1, R2, and R3, and I will be the same value because there will be no junction at all. So I will be 0.032 times with 250 times with 150 and times plus and times with the set 350. So you will see that V1, okay, V1 is here. So I will do the this is V1 and this is V2 and this is V3. Look at the value. V1 are 8 volt, V2 is 4.8 volt, and V3 will be 11.2 volts. And if you want to make sure that your values is correct, okay, try to add everything. Try to add everything, and everything of V1 plus V2 plus V3 must be equal to 24 volts. So that's how we check our answers. Okay, we have V1, V2, and V3, and all values of V will be based on I times R. I times R. Okay, very good examples in determining the resistors. Okay, now we look at the resistors that in parallel. Okay, when in parallel. Remember, in parallel, okay, look at I. So in here we have I total going out from the positive terminal, and it goes and until it reach this point, let's say point A. Okay, then this is the junction that we are talking now. Junction. So the junction means at that point, particular point, I will be, okay, I will be split. Okay, I will be split into different road. Okay, I will be based on R1. So this one is I1. R2 will be I2, and of course I3 at R3. So there will be the different value of I. And afterwards, when we reach at this point, let's say point B, and we will get back the I total. So at this point, the value of I total, okay, I total will be based on I1 plus I2 plus I3. Okay, I1 plus I2 and plus I3. So in the end, what is the same? Okay, remember, the potential difference is measured from this point to this point. Okay, and of course, if you do have 12-volt batteries, okay, at here, so this is the where the 12-volt batteries will flow. Okay, from this point, let's say C and D. So from point C to point D, the potential difference measured will be 24. And of course, yeah, we can also get the using the same things from here to here. This is also 24 volts. This point to this point is also 24 volts, and this point to this point is also 24 volts. If, oh, sorry, 12 volts, 12 volts. Okay, 12, 12, 12, because I see 12 here, right? If, like that. Okay, so in this case, VT, okay, V total will be equals to V1, will be equals to V2, will be equals to V3. Okay, so remember I is what? I is equivalent to IT. What is IT? Remember, I equals to V equals to R equals to V. So I equals to V over R. Okay, so we can have I1 plus I2 plus I3. So what is I1? I1 is V over R1 plus V over R2 plus V over R3. And we will factorize the V. So that should have V equivalent to I over R1 plus I over R2 plus I over I over R3. So this one is R equivalent. This one, everything inside the bracket is the R equivalent times with the V. V without V1, V2, V3 because all value will be the same. So still, we are still proposing that in order to solve the problems of the parallel circuit, we should have also R equivalent. Number one is to find R equivalent, and number two is to find the I total. Because in here, for the parallel circuit, okay, you can see that R1, R2, R3 are arranged as that they are parallel to each other, meaning that parallel to the batteries. So in order to do that, you should reduce this part. Okay, we should reduce the part of R1, R2, and R3 with only left REQ equivalent. Okay, so we need to understand in order to get the R equivalent, so we should write, we should calculate the 1 over. Remember to reciprocal back the value in order to get R equivalent, because R, another 1 over R equivalent is 1 over R1 plus 1 over R plus 1 over R3 and so on. So this is equivalent to 1 equivalent. Remember to reciprocal back because we want to adjust R equivalent in here. So we will simplify the equations. We will simplify the electric circuits by combining I total, okay, and also R equivalent in order to get VT. Okay, VT is equivalent to I total times R equivalent at any point. Okay, there will be another part of. Okay, now we made a look at this example. 4 resistors are connected as shown in figures. Find the equivalent resistance between point A to point C. Between point A to point C. Okay, let's measure the equivalent resistance. Measure first. A is the R equivalent. How to measure it? Okay, how to measure it from point A. This is point A. This is point C. How to measure the R equivalent? So we actually, the easiest thing to calculate the R equivalent. Okay, first of all, please find where is the parallel circuit. So I can think this is the parallel circuit, while this is just a simple series circuit. So 8 and 4 ohms are series to each other. So we need to simplify. Okay, simplify. Simplify 6 ohm and also 3 ohms into 2 ohms. Okay, 1 over 6 plus 1 over 3, and you reciprocal back, you will get 1 over 2. So your reciprocal to get 2 ohms. So 2 ohms, this one you can plus 8 times 4. 8 times 4 is equivalent to 12. So you can get here 12 plus with 2. So you will get 14 R. So this is the R equivalent, 14 ohm. And the part B is what is the current in each resistor if 40 volt batteries is connected between A and C. Okay, that's okay. Right. So what is the current in each resistor? First of all, okay, look at that what they did. Okay, first they did the find the R equivalent. And what happened next is they find the I total. Okay, what is I total? Remember, I total is V total over R equivalent. Okay, what is V total? 42 volts. Okay, 42 times the R equivalent, 14, and we'll get 3 ampere. So of course, when we try to combine it, let's say if you do have positive and negative terminal, so I total will goes to this point and will flow in series for 8 ohms and this one flow in series and 4 ohms also flow in series. So it will flow 3 ampere at 8 ohms, 3 ampere at 4 ohms, okay, 3 and 4. But for 6 and 3, okay, originally it is a parallel circuit. Okay, originally it's a parallel circuit, so you need to understand, you need to make sure that I is also flowing, I is also flows from to 6 ohms and also 3 ohms. But at this point, okay, the I will split up I1 and 2 and I2. Okay, I1 and I2 they will split. So of course we want to measure first what is the voltage. Okay, what is the voltage? I'll use another color. Voltage at 6 ohm and also at 3 ohms because voltage are the same at this particular box because they are parallel to each other. So in order to do that, we need to find what is the V. That's why they calculated here I is 3 ohms times with 2. Okay, how can they get 2 here? Okay, based on this part. Okay, based on this part, this is a 6 ohm, 6 volts. Okay, because I will flow at 12 and I also will flow at 2. So it's considered as 6 volts of battery. So meaning that 6 volt from here and so 6 a lot of volts. 6 minus 42 minus 6 is at around 36. Okay, 36 volts at here and just 6 volts here. And of course, if you add 36 to 6, and you will get 36 plus 6, you will get 42 volts. So this is the V total. Okay, so 6 volts up here and 6 volts down here, then we'll get I equivalent to 1 ampere and also 2 amperes. Okay, it's not the same because it's a parallel. And this one needs a lot of exercise and a lot of trains in order for you to understand quite well. Okay, I think we will continue later. Uh, maybe we continue next week, inshallah. Okay.